Greetings. This video has been made as a part of TI Analog Design Contest 2014. Our project is titled Intelligent Load Management System with Optimal Use of Solar Energy. We are from Amrita School of Engineering, Coimbatore. We are a team of 5 members guided by assistant professors Mr. Shivraj and Mr. Vijit. This video will brief you about the working of the circuit, followed by a clip of our working system. This is the system level architecture of our project. The project can be divided into two systems, the battery management system and the inverter system. Buck boost converter is the heart of the battery management system. This controls the current flowing through the battery depending on the state of charge of the battery. A set of voltage and current values are monitored using their respective sensors, which is further processed using an analog to digital converter. Moving on to the inverter system, which is used to basically convert the battery voltage to AC. This output is filtered and stepped up to 230 volts, which either powers the load or is directly synchronized with the grid. An interactive GUI is designed for the user to monitor and control the system parameters using UART communication protocol of the microcontroller. The solar panel seen here is PVL68, manufactured by Unisolar. This is installed in Amrita Vishwavidyapeetham, Coimbatore. The panel has the following specifications. It is a 24-volt panel having a short circuit current of 4.1 ampere. It can supply a peak power of 53 watts under nominal operating cell temperature of 43 degrees Celsius. We've used two of these panels connected in parallel to provide high charging current. This depicts the parallel connection made. As mentioned earlier, control of the buck-boost converter plays a major role in the battery management system. Schematic diagram of a buck-boost converter is shown here. The values of inductor and capacitor are designed considering the battery rating. Solar panels are connected to the input of the buck-boost converter. The converter bucks the voltage if given a duty ratio less than 0.5, else it boosts the input voltage. Duty ratio of the control pulse is triggered using a microcontroller. As seen from the characteristics, the solar panel acts as a constant current source whose terminal voltage changes according to the load connected. By varying the duty cycle, Thevenin's resistance as seen from the solar panel can be controlled. Thus, with the optimum duty cycle, the operating point of the solar panel can be brought down to knee point. It is further noted that the power obtained from the solar panel is maximum at knee point. The screen shows the hardware implementation of a buck-boost converter. The various ICs used to implement the circuit are marked. The ones marked in red color are ICs manufactured by TI. This board uses 4 TI ICs, namely UA7808, UA7805, CSD18504KCS, and UCC37322P. The optocoupler IC is manufactured by Fairchild. Since the controller is connected to various points in the system, the ground of PWM pulse given to MOSFET needs to be isolated from the ground of the controller which might be connected elsewhere in the system. An opto-isolator is used to achieve this. A MOSFET driver is inserted between the isolator and MOSFET, which helps in providing power to drive the MOSFET and also reduce the switch on time and switch off time of the MOSFET. The slide will explain the inverter system in our project. Figure 1 is the inverter circuit. The 12 volt AC output obtained from the circuit is fed into the narrow bandpass filter using the TIIC OPA549. Transformer after the filter circuit increases the voltage from 12 volt to 230 volt. The pulse required to drive the MOSFET is obtained by comparing a sine wave and a triangular wave whose amplitude and frequency are designed. The desired gate source pulse for the MOSFET is shown in the graph. The hardware of the inverter is implemented and ICs are marked. The MOSFET used here is CSD18504KCS, manufactured by TI. Op-amp UA741 used to generate a triangle wave, and comparator IC TLV37021 is used to compare the triangle wave with sine wave to produce pulses.
This video has been taken in our college, Amrita University, Coimbatore. There are totally 8 panels installed in the campus. We are using 2 of these connected in parallel to run our system. On a sunny day, the average intensity varies anywhere between 650 and 800 watts per meter square. These panels were manufactured by Unisolar. It is a 24-volt panel with a short circuit current of 4.13 amperes. All cables of the panels are bundled together and run through these pipes shown. They are organized into a control board where the configuration of all these 8 panels can be changed. The power output of the solar panel in terrace is transferred to the lab through the switchboard. We have connected 2 meters in the input side. One meter shows the voltage across the solar panel and the other shows the current drawn from it. As you can see, the open circuit voltage of the solar panel is 20.8 volts. Now when the switch is closed to connect the load, the voltage of the panel drops depending upon the initial duty ratio and load connected. The controller executes MPPT algorithm in order to make the solar panel to operate at maximum power. The power drawn from the solar panel is 75.6 watts. This logic is implemented with the help of buck-boost converter. The MOSFET acts as the switch which is controlled using ARM Cortex-M3 processor. The power is delivered to the battery with minimum loss. The average terminal voltage of the battery is around 13.3 volts with the charging current equal to 5 amperes. The current flowing into the battery is converted to an equivalent voltage to be fed into the ADC module. Similarly, a voltage divider circuit is used across the battery to determine the battery terminal voltage. Along with the ADC conversion, the processor also implements MPPT algorithm and controls the pulse given to the buck-boost converter. The ADC values are shown in Code Composer Studio. A GUI is made to continuously monitor circuit parameters. The GUI is programmed in MATLAB. The UART feature in the controller reads various circuit parameters, computes SOC, and sends these values via UART to the computer. A serial port is opened in MATLAB to receive and display these values. A stop button is provided to stop receiving data and quit the GUI. SOC is continuously updated and displayed. Since we employ MPPT before 80% SOC and constant current after 80% SOC, the current charging mechanism is displayed. The interface also allows the user to connect the output switch of inverter to either load or the grid. Number of times the battery has been charged and discharged is saved. As you can see, the instantaneous solar panel voltage is displayed along with the battery charging current and battery voltage. The user can force SOC calculation. In such case, battery is disconnected, terminal voltage and second and fifth minute is taken, Euler characteristics is applied, and SOC is recalculated to calibrate the SOC obtained from Coulomb counting method. Because the force SOC process takes 5 minutes, the video is fast forwarded. The SOC is 79.99. When the SOC reaches 80%, you will see that the charging mode changes from MPPT to constant current mode. Now the solar panel is not operating at the maximum power point. The buck boost is controlled such that the charging current is maintained at constant value of 2 amperes. The multimeter readings are also shown parallelly. Now we are going to see the inverter circuit. This is the fabricated printed circuit board. The 12-volt battery acts as a supply to the board. The square wave input to the board is given from the ARM Cortex-M3 processor. The square wave is fed into the integrator circuit using UA741 op-amp to get the triangular wave. The sine wave is obtained from the supply via step-down transformer as a reference wave. These two waves are compared using TLV37021, whose output is given to 7404 NOT gate IC to get the complement of the input signal. These two opposite pulses are given to two op isolators 6N137. The four outputs are fed as a gate pulse for the four MOSFETs, which are provided with heat sinks. The output of the inverter is given to a fourth order band pass filter. The 12-volt battery charged by the buck boost converter is given as the input to the inverter. The output of the system is as shown here. This is the unfiltered output and this is the filtered output. The frequency can be observed to be 50 Hz.